Tools for Engineering Humans. Introduction. Since the dawn of time, humans have been shaped by technology. To survive, humans built tools and re-engineered the environment and themselves. The roots of contemporary techno-social engineering are ancient. Accordingly, in this chapter, we provide a historical primer on the transformative power of tools. Tool use, the basics. While the myth persists that technology is applied science, humans have always developed and used tools, even during pre-scientific times. Some define the human essence by this capability, characterizing us as Homo faber, beings who make and use tools. From this perspective, tool use enables us to accomplish ends that otherwise would remain out of our reach. Many of these ends continue to elude other species on the planet. There is considerable evidence of non-human tool use, even quite sophisticated techniques and inventions, among animals such as crows, chimpanzees, and cephalopods. Nonetheless, we don't have to worry about any of them starting a nuclear war anytime soon. Technology doesn't always do what we want it to do. Inventors can't always determine how a technology will be used once it's integrated into society. To believe otherwise is to commit the mistake known as the designer's fallacy. Technology use routinely involves unintended consequences and trade-offs. Take the discovery of fire and early inventions that applied it to keep people warm and cook meat, which is a quick source of protein. The process had obvious benefits for our ancestors, including profound cognitive ones, but the Promethean gift also posed risks. Fire can burn people, possessions, and shelters. Most importantly, the development and use of tools to make and manage fire shaped who we are and who we are capable of being. As anthropologists and historians have explained, these tools open new possible paths for humans to live and develop. Other tools have done the same. Yet over time, we've lost many capabilities by learning to solve problems with newer tools. Our predecessors could do many things that most of us simply can't do anymore. Know anyone who uses dead reckoning to navigate a boat? That's a pre-GPS orientation to determining positioning, revolving around factors like time, direction, and speed. Or imagine if, in the future, the only cars that exist are autonomous, self-driving models. If they collectively went on strike, how many would be able to ride a horse to work, or pilot a dumb automobile after stealing it from a museum? Tool use has also expanded our capabilities. Delegating tasks to technology has freed up time and resources and enabled us to move on to new and often more advanced problems. Keeping the innovation cycle going requires imagining, creating, and using new tools. Consider the trajectory of fishing tools as a progression from spearfishing to using a fishing pole to using nets, and so on. Along the way, capabilities have been gained and lost. At one time, many humans had considerable skill in handling a fishing spear. Doing so was necessary to obtain food. Over time, that skill gradually became less useful. At some point, a fishing pole proved more efficient, and that efficiency ended up paling in comparison to subsequent large-scale fishing from boats with nets, a historical turn that turned pole fishing into a recreational hobby, rather than a professional endeavor, for many cultures. In the end, progress in fishing appears to be a net gain in terms of both efficiency and capabilities. Less fishing effort by fewer people yields more fish for consumption, and, as a result, people in a historically based fishing community can diversify their skills and learn to use other tools. Upon closer inspection, however, complex trade-offs become apparent. Displaced fishermen who cannot find work doing other jobs are a problem. Not everyone can transition from skill to skill, not least because training can be too costly and time-intensive. In some contexts, eroded familial and community traditions lead to a loss of social identity and capital. We should be skeptical of overly rosy narratives about how the future of automation will liberate us to spend more time doing artistic and related endeavors. While it's tempting to assume innovation yields ever-increasing net gains, we must avoid being lulled into complacency by simple and comforting explanations. Patterns of this sort aren't uniform or inevitable. They can change, be localized, and even be manipulated to affect the distribution of gains and losses. There are always winners and losers as wealth, power, and capabilities concentrate and dissipate. Shaping and being shaped by tools. As media scholar John Culkin put it in his rephrasing of a famous Winston Churchill quote, "We shape our tools, and thereafter, our tools shape us." This truism seems banal. It's easy to state, but much more difficult to employ in a manner that elucidates and enables evaluation of tools or humanity. We need to understand how we shape and get shaped by our tools. This mutual shaping occurs on an existential level through self-understanding and modeling. Philosopher John Searle thus observes, "Because we do not understand the brain very well, we are constantly tempted to use the latest technology as a model for trying to understand it. In my childhood, we always assumed that the brain was a telephone switchboard. Sherrington, the great British neuroscientist, thought that the brain worked like a telegraph system. Freud often compared the brain to hydraulic and electromagnetic systems. Leibniz compared it to a mill, and I am told that some of the ancient Greeks thought the brain functions like a catapult. At present, obviously, the metaphor is the digital computer. On other levels, the dynamic constitutive relationship between humans and tools requires that we look beyond the particular function of a tool. According to Weizenbaum, whatever their primary practical function, tools are necessarily also pedagogical instruments. In other words, our tools allow us to teach each other about the tools and their functions, but also to teach us about who we are, what we can do, what is possible, and who we may become. Tools become part of the environment that shapes our beliefs, preferences, and capabilities. In the history of technosocial engineering, language may be the most important tool ever invented. Historian Yuval Noah Harari claims that three major revolutions shaped the course of human history: the cognitive revolution, the agricultural revolution, and the scientific revolution. The cognitive revolution, which occurred about 70,000 years ago, involved the emergence of new ways of thinking and communicating that relied on fictive language. While many animals communicate, examples being the buzzing of bees and the howls of monkeys, only humans have developed language capable of describing things that don't exist. Imagined things. Fictive language is important because of the collective affordances it provides, especially in our ability to coordinate activities and work collectively in flexible ways. With fictive language, humans could create common myths and construct complex social institutions, such as churches and governments. People believe in the existence of laws, justice, human rights, for example, but none of these things exist outside the stories that people invent and tell one another. Language begets myths and large-scale human cooperation or subjugation. Myths sustain empires. Remarkably, on 2 consecutive pages of his book, Harari displays the Code of Hammurabi and the Declaration of Independence. Both claim to be rooted in universal and eternal principles of justice. Nevertheless, the code proclaimed a social hierarchy among superiors, commoners, and slaves, while the Declaration proclaimed all are created equal. Neither is natural or objectively true. Both are powerful myths, imagined orders made possible by the tool of fictive language. The agricultural revolution also profoundly transformed human societies across the world. Unlike foraging societies, agricultural societies needed to manage huge amounts of mathematical data. Human brains were not up for the task, forcing our ancestors to develop tools to store and process data. The Sumerians developed a written language, initially limited to facts and figures. At first, this partial script did not cover the whole spoken language, but over time, this changed. For example, cuneiform emerged as a full script allowing humans to speak not only to those around them, but also across longer distances and even generations. The scientific revolution introduced an array of powerful tools, starting with a change in mindset. Embrace science as a means for transcending our natural human ignorance. As humans began to accept their own ignorance, they invested more and more resources in scientific research to explore the unknown and use the acquired knowledge to develop new tools. Science incorporates systematic observation with experimentation, new forms of imagination, theorizing, and the logic and language of mathematics. Isaac Newton's 1687 masterpiece, The Mathematical Principles of Natural Philosophy, might be the most important book in modern history. Newton's theory was a powerful, general-purpose tool. It could be used to explain all sorts of physical phenomena, from apples falling from trees to the trajectory of artillery. It reflected and contributed to our changing mindset. Newton showed that the book of nature is written in the language of mathematics. At a macro level, science has become a powerful techno-social engineering tool that rivals religion. For some, it has become a secular form of salvation. Instead of praying to God or the gods for help with some calamity, some place their faith in science's ability to solve all problems. Take global warming. Instead of having confidence in divine intervention or a radical change emerging in every person's ecological sensibilities, some hope that global warming can be mitigated through powerful forms of geoengineering, literally re-engineering the Earth. Tools are also products of human imagination. We create little without first imagining that we can create it. Yet tools also shape our imaginative reconstruction of the world. Tools are pregnant symbols in themselves, meaning that they symbolize the activities they enable. The fishing spear is a tool for fishing, and it represents the capability associated with its use. As it comes or goes, so does our imagined construction of the world and ourselves within it. Joseph Weizenbaum discusses a series of examples of this phenomenon, ranging from spears, the six-shooter, and other weapons, to ships of all kinds, to the printing press, the cotton-picking machine, and industrial machines. He discusses tools for measurement, such as telescopes and microscopes, and various other prostheses that extend human power, reach, and control over the environment. With each of these examples, humans gain and lose functional capabilities while their imagined world and their place within it are transformed. Perhaps the paramount change that took place in the mental life of humans was our perception of time and space. For most of our time on Earth, humans perceive time as a sequence of constantly recurring events, rather than a collection of abstract units, such as hours, minutes, and seconds. The clock changed everything. It was the first autonomous machine, not a prosthetic extension of human power. As the historian and philosopher Lewis Mumford observed, the clock disassociated time from human events and helped create the belief in an independent world of mathematically measurable sequences, the special world of science. The clock transformed human perception of nature and consequently humanity's role as creature of and living in nature to nature's master. Weizenbaum not only connects the clock to the rise of scientific rationalism, but he also links the clock to the fall of direct experience as a guide for human judgment and knowledge. It is important to realize that this newly created reality was and remains an impoverished version of the older one, for it rests on a rejection of those direct experiences that formed the basis for, and indeed constituted, the old reality. The feeling of hunger was rejected as a stimulus for eating. Instead, one ate when an abstract model had achieved a certain state, such as when the hands of the clock pointed to certain marks on the clock's face, and similarly for signals for sleep and rising, and so on. Historians, economists, science and technology studies scholars, and experts from various disciplines have examined other transformative tools that shaped the developmental path for human society over the past few centuries. The steam engine transformed human society, as did the telephone, the automobile, radio, television, and many other forms of technology, and today we have the computer. Weizenbaum fixates on the computer as a symbol and implementation of the dramatic transformations at the end of the 20th century. Like the clock, the computer is an autonomous machine that can run on its own and perform various functions without needing human intervention. Like the clock, the computer has transformed us. Initially, computers simply performed existing computing tasks more rapidly. Calculations done by humans in their heads with paper and pencil, slide rules, or tap cards could be done more efficiently with computers. But, as is often the case with transformative tools, the range of uses for the computer expanded substantially with experience. Problems that were comprehensible in the language of computation could be tackled with computers. Computers gradually became integrated into an incredibly wide array of business and government processes and systems, becoming part of the structures upon which these systems depended, part of their background environment. Business decisions and, more importantly, the methods for making business decisions, such as systems analysis and operations research, grew increasingly reliant on the power of computers. As the power of computers grew, so did the perceived power of the methods and consequently their prestige and scope of application or their domain. The expanded scope of systems analysis, operations research, and a host of related computer-aided decision-making tools extended their influence on society. They became their own fields and entered the mainstream. Fetishized computers and idealized computation. Weizenbaum makes a remarkable observation that resonates with much of what we say in this book. He states, "The interaction of the computer with systems analysis is instructive from another point of view as well. It is important to understand very clearly that strengthening a particular technique, putting muscles on it, contributes nothing to its validity. If a computer greatly improves the carrying out of calculations used to cast a horoscope, performing a series of complex symbol manipulations, etc., and doing so much more rapidly and efficiently than an unaided human astrologer, the improvement in the technique of horoscope casting is irrelevant to the validity of astrological forecasting, and thus, if astrology is nonsense, then computerized astrology is just as surely nonsense." Weizenbaum identifies a fundamental problem. We have fetishized computers and other tools, and as a result, we have reified complex systems that have no authors, about which we know only they were somehow given us by science and that they speak with its authority and permit no questions of truth or justice to be asked. The science he refers to is a type of rationalism and instrumental reason that can be boiled down to computability and logicality. For example, he criticizes B.F. Skinner for elevating behavioral science over common sense, and this means failing to appreciate a common sense informed by a shared cultural experience, and that balks at the idea that freedom and dignity are absurd and outmoded concepts. Weizenbaum sensed a shift in the pattern in the coevolution of humans and our social and technological tools. There seemed to be an all too convenient marriage between means and ends. The tools, computers, systems analysis, science, instrumental reason, work together synergistically to define reality, just as the light under a lamppost defines the territory within which a drunk might look for his lost keys. Instrumental reason, triumphant technique, and unbridled science are addictive. They create a concrete reality, a self-fulfilling nightmare. It's difficult to appreciate how powerfully the tools we develop shape us. One of the most important ways is by shaping our imagined reality, our very beliefs about ourselves, and our preferences and values. If the ends worth pursuing are determined by our tools, by their constructed reality, the contours and contents of the lit space under the lamppost, then nothing less than our very humanity may be at risk of being whittled away. Our imagination could become bounded by the constraints embedded in the tools and the logics that they perpetuate. We are not there, at least not yet. In many ways, experience suggests that our tools generally have expanded our horizons. This is especially true when it comes to knowledge. Nonetheless, we must remain vigilant and continue to examine our tools, our reliance on them, and what ends might linger just beyond the light. Let us put the key point simply, as Weizenbaum did. Problems comprehensible in the language of computation, in theory, can be solved with computers, systems analysis, science, instrumental reason, and so on. Conversely, problems incomprehensible in the language of computation, by definition, cannot. Weizenbaum explains how many incomprehensible problems are improperly assumed to be comprehensible. Justice, for example, is not in and of itself comprehensible in the language of computation. Many different conceptions of justice have been articulated. None of them are fully reducible to computation problems. Recall Harari's comparison of the two codes of justice, Hammurabi's Code and the Declaration of Independence. The subject matter of both uses numerical relationships to express conceptions of justice, and one might argue that the codes aim to reduce justice to a computational problem, but neither really does. Both rely on the prior judgment of the collective human society, or those in power, to construct the imagined reality reflected in the codes. Humans set the baselines for justice. Similarly, policymakers and value theorists may frame social choice problems in terms of social welfare functions and thereby structure choices and trade-offs in a manner that seems quantitative, formulaic, and possibly reducible to problems comprehensible in the language of computation. However, beneath the framing itself are a host of human judgments about values and relative weights that set the baselines necessary for computational processes to run their course. A major social problem is rooted in the imperialism of instrumental reason and the improper assumption that all problems are comprehensible in the language of computation, and thus can be solved with the same set of social and technological tools. This assumption sometimes results from erroneous understanding of problems, but also from myopic infatuation with the power of our tools. We might modify Culkin's phrase as follows: we shape our tools, fall in love with them, and thereafter, our tools shape us. Weizenbaum's argument remains fundamental, particularly as we identify ever more powerful means for solving problems comprehensible in the language of computation. Extending the concept of the designer's fallacy, we label this issue the problem of engineered determinism. What we mean to evoke by the term is the idea that society can engineer in a deterministic fashion a world that operates deterministically. This is not to say the world is naturally deterministic or predetermined by fate or natural physical processes. Rather, it is the grand hubris that we can socially construct a perfectly optimized world if we only have the data, confidence in our tools, and willingness to commit. Against the imperialism of instrumental reason, a chapter in Weizenbaum's book opens with a parable of how the enormous power humans have attained through the tools of computerized science and technology have left humans impotent. To hammer home the point, he quotes the historian Studs Terkel. For the many, there is hardly concealed discontent. "I'm a machine," says the spot welder. "I'm caged," says the bank teller, and echoes the hotel clerk. "I'm a mule," says the steel worker. "A monkey can do what I do," says the receptionist. "I'm less than a farm implement," says the migrant worker. "I'm an object," says the high fashion model. Blue collar and white call upon this identical phrase. "I'm a robot." Powerful as Weizenbaum's account is, it remains incomplete. It has influenced our work substantially, as we've hopefully made clear, but Weizenbaum focused on two related sets of tools, one technological and the other social. The technological tool set centered on the computer. He emphasized its symbolic role. Throughout this work, we'll discuss other tools within that set, such as communication networks, algorithms, and big data. Taylor's scientific management of human beings. There is something fundamental missing, or perhaps implicit, in Weizenbaum's account that we need to draw out. It's the paradigm shift that occurred at the turn of the 20th century with the emergence of Frederick Taylor's theory of scientific management, commonly referred to as Taylorism. Taylor revolutionized the relationships between management and labor, and it's no surprise that all the people in the Studs Terkel passage that Weizenbaum quoted were workers. In his biography of Taylor, Robert Coniglio offers the following description. Taylor was the first efficiency expert, the original time and motion man. To organized labor, he was a soulless slave driver, out to destroy the working man's health and rob him of his manhood. To the bosses, he was an eccentric and a radical, raising the wages of common laborers by a third, paying college boys to click stopwatches. To him and his friends, he was a misunderstood visionary, possessor of the one best way that, under the banner of science, would confer prosperity on worker and boss alike, abolishing the ancient class hatreds. We connect Taylorism to Weizenbaum's account for a few reasons. First, the link strongly supports Weizenbaum's observations about the rise of systems analysis, operations research, and computer-assisted decision-making within business management circles. It even buttresses Weizenbaum's emphasis on the importance of the clock as a techno-social engineering tool. After all, Taylor's system depended heavily on efficiency experts using stopwatches to conduct time studies, a critical source of data used in scientifically managing workers. Second, the connection helps explain the rise of instrumental reason and scientific approaches to managing human beings and their social relationships in the workplace and elsewhere. Third, the association focuses on a set of techniques that preceded and did not depend on the computer. These techniques have been strengthened greatly by computers and adjacent technologies such as sensors, data analytics, communications networks, and so on. Yet the normative validity or legitimacy of the techniques must be evaluated independently, and, to do so, we must resist the pull of fetishized innovation and unwarranted claims of technological inevitability. Taylor developed his techniques, his theory of scientific management of humans in the workplace, in the late 19th century and early 20th century. Taylor saw substantial inefficiencies in factories and other workplaces, and he attributed many of the inefficiencies to mismanagement of labor. As a young man, Taylor had worked as a shop foreman, attempted to get the most out of his workers, and begun to diagnose the inefficiencies he observed as a product of poorly structured incentives, unmotivated and sometimes shirking laborers, and, perhaps most importantly, a tremendous knowledge gap that rendered management ineffective. Managers knew too little about the workers, their tasks, their capabilities, and what motivated them to work. Over decades and across different workplaces and even industries, Taylor carefully studied workplaces, workers, and their work. He examined minute details of tasks performed, and based on the data he collected, sought to optimize performance in terms of increased efficiency and productivity. Taylor's system was generalizable. In other words, his system was not limited to a particular workplace, nor was it limited to any set of time and motion studies. At one level, Taylor's scientific management system is a type of data-dependent technology. Taylorism is one of the best early examples of data-driven innovation, a concept currently in vogue. Taylor's system included the techniques for both gathering data and putting such data to use in managing people. Taylor's system thus encompassed the surveillance techniques employed by the efficiency experts, their use of stopwatches and careful visual observation of task performance under varied incentive schemes. For example, he would offer a worker being studied a much higher wage than the prevailing market wage to test worker capability and task performance under different conditions, and, if possible, push prevailing views about what workers could accomplish and increase productivity. Taylor and his disciples relied on personal observations written in notebooks and careful analysis of various inputs, outputs, processes, and procedures across the many workplaces they studied. Taylor's critics emphasized that Taylor's scientific management was anything but scientific. They alleged, accurately in many cases, that Taylor's prescriptions for management often had an ad hoc flavor to them. When the data was incomplete, Taylor relied on his own judgment, which amounted to little more than a fudge factor or unwarranted exercise of managerial discretion and could not be considered scientific. Yet the managerial data gaps would close. 20th century technological innovations, ranging from the computer to the camera, have dramatically upgraded the capability of managers to gather, process, evaluate, and act upon data. Not surprisingly, Taylorism spread like wildfire across industries and beyond the factory floor, to hospitals, schools, and various other contexts. As Coniglio put it, Taylor's credo of rational efficiency has burned its way into the modern mind. Taylorism is an applied version of the instrumental reason and rationalism discussed by Weizenbaum. Consider how Taylorism defines both means and ends. As a technology or management technique or system, Taylorism is obviously branded as a means. The problem to be solved also was unambiguous. Inefficiencies plagued the workplace, leading to waste and lost productivity. Taylorism and Fordism are famous both for their underlying objective, namely to increase efficiency, quality, and productivity for the ultimate benefit of managers, owners, and capitalists, and means, specifically by managing factory workers in various ways that get them to behave like machines. Deeply embedded throughout Taylorism, the ends of productivity and efficiency are not only assumed to be paramount, but also to be comprehensible in the language of computation. That is the heart of Taylor's claim that his system constituted scientific management. It is reflected throughout the system itself. Workers were, in fact, conceived as inputs, cogs, resources, etc. Their work was broken down, analyzed, and programmed. Taylor and his disciples assumed it was all comprehensible in the language of computation. At a fundamental level, Taylorism was a revolutionary system for engineering humans. As Taylor famously declared, "In the past, the man was first. In the future, the system must be first." The assembly line is a particularly salient and culturally recognized example. An assembly line is a manufacturing process involving the progressive assembly of parts into a whole product, where the semi-finished assembly moves from one workstation to the next in a linear fashion. While assembly lines predated Taylor and Ford, Ford famously optimized the process for mass production. Fordism combined product standardization, systematized use of assembly lines wherein unskilled laborers use special-purpose tools at different stages, and the principle that workers should be paid higher living wages to both provide better incentives and enable them to purchase the products they made. A critically important aspect of this type of techno-social engineering is the environmental nature of the means, the way in which the managers employing the management practices advocated by Taylor and adapted by Ford reconstructed the physical and social environments within which their workers worked. Managers could leverage control over the environment to control those within the environment in various subtle but powerful ways. Similar to how the clock reconstructed our environment and us, time and motion studies fuel task and schedule management in the workplace. As Harari describes, modern industry sanctifies precision and uniformity. For example, in a medieval workshop, each shoemaker made an entire shoe, from sole to buckle. If one shoemaker was late for work, it did not stall the others. However, in a modern footwear factory assembly line, every worker mans a machine that produces just a small part of the shoe, which is passed on to the next machine. If the worker who operates machine number 5 has overslept, it stalls all the other machines. To prevent such calamities, everybody must adhere to a precise timetable. Each worker arrives at work at exactly the same time. Everybody takes their lunch break together, whether they are hungry or not. Everybody goes home when the whistle announces that the shift is over, not when they have finished their project. The factory thus not only produced whatever widget the company eventually sold, such as Harari's shoes or Ford's automobiles, but it also produced machine-like humans, sometimes referred to automatons. Conegill states, "Both Taylor and Ford raised production, cut costs, and reduced the judgment and skill needed by the average worker. A Ford plant differed from a Taylorized plant in certain respects. In either case, the worker was left with 8 or 10 hours whose minute-by-minute course was more closely prescribed and scrutinized than ever. After Ford and Taylor got through with them, most jobs needed less of everything. Less brains, less muscle, less independence." Taylorism criticized yet expanding. Critics of Taylorism recognized and railed against these effects on workers, but architecting the environment, optimizing it really, to achieve these particular effects is the technological innovation to note. The Industrial Revolution turned the timetable and the assembly line into a template for almost all human activities. Soon, schools too adopted precise timetables, followed by hospitals, government offices, and grocery stores. These are interesting examples because they define and are defined by the physical spaces, social institutions, and increasingly, technologies that together constitute particular environments designed to engineer humans. Schools engage in techno-social engineering of humans. Communities rely on schools to educate and transform their children. Like a factory, a school transforms a combination of inputs into socially valuable outputs. That transformation is the result of a series of internal processes. It may be disconcerting to think of schools as mere factories, children as inputs or outputs, teachers as factory workers, and so on. Still, Taylorism has had a profound impact on the educational workplace. In fact, the application of principles of scientific management within the structure, organization, and curriculum of public schools in the US became dominant in the early 1900s. Like scientific management more generally, Taylorism in public schools may have waxed and waned over the past century and across different regions, but it has resurfaced as teachers' classroom practices are increasingly standardized by high-stakes testing and scripted curriculum. Education scholar Wayne Au and others have examined in detail how the incredibly fine-grained scripting, or micromanagement, of teachers' work neatly fits with the Taylorist logic. The school as factory metaphor is wonderfully exploited in Pink Floyd's The Wall, which vividly illustrates the worry that schools can be totalitarian environments architected to construct machines rather than humans. Schools need not and should not be built and run this way. Another ideal vision casts schools as environments that enable children to develop a range of human capabilities, including, for example, reason, reflection, introspection, emotional intelligence, sociality, and so on. For many schools, this is aspirational. Nonetheless, the social engineering that inevitably takes place in schools spans a continuum with the dystopian factory of the wall at one extreme and the utopian ideal at the other. Schools in the real world occupy intermediate positions on the continuum and can be evaluated in terms of their position, which may change over time. Without delving into education policy debates, we note that one modern trend in education is to import various surveillance, computation, and communication technologies into the schools. It is important to examine how these technologies may subtly affect the environment within schools. Schools tend to evaluate each technology on its own, performing a truncated cost-benefit analysis in the face of declining public funds and partially blinded by fascination with the power of new technology. Each incremental step to adopt a new technology may appear to be cost-benefit justified, but, in the aggregate, schools may be heading in the wrong direction on our hypothesized continuum. This is one example of humanity's techno-social dilemma. Today, even though the assembly line defines surprisingly little of modern manufacturing, Taylorism is pervasive. Taylorism had its ups and downs across business schools, management consultancies, and factory floors throughout the 20th century. Some companies and even industries moved away from it to alternative systems for managing labor. Nonetheless, the basic principles of Taylorism have become deeply embedded in how society conceptualizes all sorts of management, ranging from businesses to government to schools to amateur athletics to child rearing. Again, Robert Kanigel put it well. Today, it is only modest overstatement to say that we are all Taylorized, that from assembly line tasks timed to a fraction of a second, to lawyers recording their time by fractions of an hour, to standardized McDonald's hamburgers, to information operators constrained to grant only so many seconds per call, modern life itself has become Taylorized. With ever-growing data about human labor, task performance, and so on, the trend in workplace surveillance and management has only grown and expanded in scope, and it is likely to continue. Until when? How far can it go? What happens if taken to the extreme? What would it mean to Taylorize human labor fully? One thing it would mean is that we would have accepted, even if only tacitly, the contention that management of human labor is a problem comprehensible in the language of computation. Another thing it would mean is that any boundary around the workplace, employment, or even the idea of work itself would dissipate because human labor is not constrained to any such boundary. Modern data-driven micromanagement of human resources, time, attention, effort, etc., across various industries is simply a form of Taylorism extended beyond formal employer-employee contexts. Like vehicles, physical space, and computing resources, human physical labor can be optimized for on-demand allocation determined by data and algorithms. The Taylorist vision of efficient management is focused on minimizing costs associated with misallocated or wasted human capital, effort, and attention. Ironically, soon, eliminating productive inefficiencies that arise from mismanagement of labor might entail getting rid of human managers altogether, and turning instead to smart technologies. There is no reason to limit technologically optimized and implemented Taylorism to traditional work, however. The logic easily extends to a much wider range of actions that depend upon human labor, time, attention, effort, etc. Whether driving a car, caring for one's children, exercising our bodies and minds, or any other human activity. In the not-so-distant future, intelligent technological systems, not necessarily sentient ones, may be deployed to maximize human productivity throughout our lives. Humans are naturally inefficient. We are often unproductive and costly to sustain. One way to understand the power of the Taylorist logic, particularly as extended beyond the workplace, is that it entails minimization of various costs associated with humans being human. For humanists, this is deeply troubling. Some will emphasize the potential upsides, rooted in increased convenience, entertainment, happiness, and welfare. They'll argue that, overall, we'll all be much better off in a world optimized to deliver cheap bliss. In subsequent chapters, we'll revisit this debate about humanity and the world we're building.